Yeah, also one thing that'd be good about tomorrow's session, and I'll record that, is I have no idea how you folks are feeling about this. You know, in undergrad, I've done it so many times that I just have an intuitive sense of what's appropriate and what's not. That's A minus A to A, or A over 2, I forgot which one I did. So when it came to a particle in the box, so this is really a weird problem when you do it this way. So remember that we solved it with A e to the ikx plus B minus ikx, where K is square root of 2me over h bar squared. And I know the camera does not do a good job. And anyway, I watched the videos and I think it's okay. It's just sometimes I can't read my own handwriting, so I'm just trying to be ultra careful about that. Okay, we're going to do harder problems today. Again, we're still kind of in undergrad land, but we're going to hit the hardest undergrad problems that we did. And then long after that, we're going to be doing more of a graduate school level. So that's why I'm a little concerned. I feel like I'm going kind of way too slow. But anyway, my problem. All right, the way we solved this sucker, we got the A and B's, which was if we set the wave functions at A and minus A equal to each other, which is equal to 0, we got that the wave function was basically cosine. And if we did the same with the derivatives, then we got the wave function was basically a sine. And that means that A is equal to B and A is equal to minus B. Now, as I mentioned, what I don't like about these problems is they're really open-ended, like a video game where you're just in a big area and maybe it's not really well defined what you're supposed to be doing. But if you happen to do the right thing, it goes well, right? So I don't quite know, and again, I really bash traditional chemistry quantum teaching. I just wouldn't know where to begin, but this is where you begin. What you're doing is in the big picture, here are the specific steps to get cosine and sine. The big picture is you're just enforcing symmetry. You're saying that the left and the right have to be identical. The values of the wave functions, we pick the endpoints because it's convenient, and the derivatives also have to be symmetric. That's what we're saying. So yeah, that's all it comes down to. And again, the name of the game is getting A and B. Last thing I wanted to point out was, well, I guess I have 2 points. Remember that we got A is equal to minus B on the second derivation, and we know that. So the wave function is essentially, and we're not worried about normalization. We've got e to the ikx, e to the ikx, sorry, I'm thinking about the camera again, e to the ikx minus e to the minus ikx. Now, you may notice that I just started calling that sine. I just said that's sine kx, and then I figured out that k was n pi over the length of the box, that's 2a, so that could be, anyway, yeah, so I just said it was sine kx. Again, k was whatever it was for n equals 2, 4, and 6, and cosine k is n pi over the length for n equals 1, 2, 3, whatnot. Okay, now does it bother any of you, this is what I want to point out, that this isn't really true. Remember, it's 2i, right? So remember, e to the ikx minus e to the minus ikx over 2i is a sine function. So when I figured this out, this is what I got, and I just called it sine. I really should have said it was 2i times sine, and then it's correct. But I didn't. Why not? Does that bother me that I didn't put that in there? What do you think? Yeah, big deal, not a big deal?
It's a constant.
Well, it is a constant, but that doesn't, so is, my cat is a cat. But what what are the implications of the fact that it's a constant?
It has no real part.
Again, you're describing but not explaining. That is true of 2i, that's correct. Again, that's a description but not an explanation. Careful of that when you answer questions, right? Undergrads make that mistake all the time. Okay, what generally goes in front of a wave function? So remember, we have slick-willy ways of figuring out whether the wave function is a sine or a cosine or an e to the ikx or e to the minus ikx and some other fancy stuff we're going to get into. What's usually in front of the wave function? Something we usually have to figure out after the fact. The normalization. Yes, the normalization. Remember that the way we set these up give us sines and cosines. Mathematicians never worried about normalization. That doesn't mean anything to them. When they have a differential equation, which the Schrödinger equation is a differential equation, and they find solutions, there's no such thing as normalization to them. Because what the hell, why would there be? Sine and cosine, or 2i times sine, that's fine. In our world, these need to be normalized, right? So the integral of this thing from minus a to a better be 1. So what do you think is going to happen to that 2i? Yeah, it just gets wiped out. It gets turned into something else by the normalization constant. I don't need to worry about it. So, I mean, we could work through that problem. I don't really care. It ends up being the thing in front of this happens to be square root of 2 over L. That's the proper normalization. L being 2a, the length of the box. That's the proper normalization for the infinite particle in the box. So again, one of the things, like, as I've gotten older, when I see someone say, oh, e to the ikx minus e to the minus ikx is sine, I just like, yeah, sure. But at your guys' age, I'm hoping that you see this kind of stuff and get a little hung up. That's because you're being detail-oriented. I'm just explaining why it actually doesn't matter. The other thing is also, think about what's your end goal. You wanted to get to the energy. And the energy is locked up in K, right? K is square root of 2me over h bar. And you know that you have a boundary condition on Kx. When K was when x was a or x was minus a, all of this had to be like 0 or 1 or I don't know, there's some boundary condition. And that means that K has to be like pi or pi halves. And so now you've got this thing, n pi halves. Now you got this thing equal to like n pi halves, something like that. I'm being very hand-wavy. And then you solve for e. So I don't care about the normalization. That's not part of it. The only thing I'm really doing this for is the energy. And that's right here. It's nothing to do with the front. Anyway, you're okay? All right, so anyway, undergrad level, the other thing I wanted to say is, actually this problem is unbelievably simple if you do the symmetry from 0 to L. So when I do undergrad, I actually have the left half at 0 and the right half at L. And then you can actually solve the problem in one step. That sucks, but it's really weird how when you're doing these problems, if you center the box at the right spot, it can make it like unbelievably easy or hard. Now the reason I centered this at 0, and again, that's actually the harder of the two, is because the other the problem on your homework and the one I'm going to do now, if you're a little bit stuck on your homework on the double box problem, what I'm going to do right now is going to unstick you. You're going to see exactly how to do this based on what I'm going to do right here. The homework's just slightly more complicated, but of the same vein. Okay, so now we're going to do the finite box. And recall also that these models, these are actually good models for molecules or atoms. So this is the potential, obviously this is the potential energy. You can think of this as like, this is the nucleus. The electron likes to be next to the nucleus. It doesn't like to be outside of the nucleus. And the particle's an electron, that's the wave function. So this is like the crudest example of an atom I could possibly pick. Or maybe like a delocalized molecule like a dye. Or like benzene, and that would almost count. Okay, now, let's see. Recall that I usually want to E less than V. So of course the barrier is V. There you go. Remember that E greater than V is just a wave that goes on forever. And if you're thinking this as an electron in an atom, If the energy is greater than the potential, that's like ionizing. That's like what happens to an atom after ionizing radiation, or a molecule after it's been hit by X-ray or UV light. That happens. A lot of people study that kind of stuff. I do. But for the most part, like when light interacts with matter, it doesn't eject electrons. Right? Visible light doesn't do that, and if it did, we'd all be dead. In fact, the ozone, the only reason people say like, well, isn't it incredibly lucky that we're all here on this planet where conditions are just right? But isn't that a self-fulfilling prophecy? If conditions weren't right, we wouldn't be here. So there you go. The conditions being that our ozone layer keeps UV light from hitting the planet, because if you got just a few more nanometers of solar hitting you, that'd kill you. Really, we're really on the edge of what light hits our planet that would kill us. Just a few more nanometers to higher energy, none of us would be here. Anyway, I thought that was interesting. Okay, now, again, this is obviously an analogy to your homework problem, and this will definitely unstick you. Okay, so in regions 1 and 3, if we're doing E less than B, then you need to solve the wave function for e to the kappa x. Remember that this is for when energy is less than V, and so these are exponentially rising or decaying functions. And kappa, I would just remind you that K is square root of 2mE over h bar squared, and kappa is 2mV minus E. And the way I remember that is V minus E versus E minus V, is that V is greater than E. Okay. Okay, and then in region, so I shouldn't have said all that. In region 2, there's no energy, there's no potential energy. So I'm not going to have kappas, I'm going to have Ks. All right, before I get to that, let me figure out for region 1. For region 1, let me tell you, I should eliminate one of these terms. Which one do you think it is? Remember, these are exponentially rising or decaying functions. We talked about this last time. I told you that wave functions decay exponentially when they hit a barrier. That means that the particle can't really enter that region. It can't, it's a barrier, right? Remember that wave function squared are probability amplitude. So what it says is, when a particle hits a wall and it shouldn't be there, it can go into it a little bit, but the probability of finding it past the wall exponentially decays, which of course is really freaking quick. So anyway, that's what these functions mean. But I can tell you that one of them, I can already do some kind of boundary condition. It's not like a mathematical one, it's more one of the practical one in my head. I can eliminate one of these terms. Which one is it? I'm talking about region 1. I can't do this in region 3. Region 3 will have a different one. That's a hint. What do you think? Let me draw the wave function. So there's the ground state. There'll only be a certain number of ones in the box before, as the next state gains energy, and the next state, the second excited state gains energy. Eventually, we'll have more energy than the potential. But anyway, for say this state, one of these is not correct. Which one is it?
D.
Which one?
Second one.
B, right. Because x is negative, right? If you're going left of 0, then you're going to a higher negative number, which makes that explode. Right, so B is 0. So boundary conditions. Okay, now, so we can just wipe that out. So tell you what, I'm just going to say this is region 1, and I'm just going to go ahead and just put the X there. Okay. Now in region 2, the reason I wanted to do that before I went to region 2, I want to call that one a B. I like that A, B, C, D. It's just a little bit better that way. Remember that is a K, you know, have a kappa, you know, have a C wave. And I can already tell that this looks like a cosine. Right, it's symmetric. Cosines are symmetric, sines are anti-symmetric. So I bet I'm going to have a even and odd set of answers. Okay. and then in region 3, I'm not going to have an A, I'm going to have a B wave, but again, so I don't mess up my letters, I'm going to call that e to the minus kappa. And again, x is going positive to infinity, so I need to have e to the minus infinity if I go infinity far away, which is 0. So that makes sense. Okay, so anyway, that's how you walk through it. And again, I don't know, when we covered Dirac notation in like 2 weeks, the starting point for all your problems is well defined, and that's very comforting. And when it comes to these problems, you should be able to write down these wave functions, but then you have to just start whittling away at it, and you just kind of have to know what to do. But to our credit, to the credit of these problems, I mean, you figure that out by just working problem after problem, and you kind of get it. Okay, anyway. All right, now, remember what I said last time, is that the way to do this is to use log derivatives. The log derivatives. The derivative over the derivative of a function over the function. That's a log derivative. Anyway, okay. So what we need to do is at x equals. We'll start with minus a. The wave function in region 1 has to be equal to the wave function in region 2. Sorry, what's wrong with me? The derivatives also have to be equal, and the wave functions also have to be equal. So remember that what I've done here is I've created a log derivative. So I started out writing the wave functions were equal, the derivatives were equal, and then I just divided the two. And that's a log derivative. Now again, I want to point out that it's this is just a clever math. If you're thinking like there's some meaning to this, there isn't. These are just boundary conditions. All you're saying is that the wave functions, like right there, they have to line up in space, and the slopes also have to be the same. They have to be smooth and continuous. They have to have the same value and the same slope. That's what that means. Big picture, I have, let's see, I've got A, B, C, D. I have 4 unknowns, right? The point of this is to get the wave functions. And that means I'm solving A, B, C, and D. Those are 4 unknowns. I have 2 boundary conditions. Wave functions equal. Slopes equal. 4 equations, 4 unknowns. And like a lot of time, 8th grade, remember 8th grade, A plus B is equal to 1. A minus B is equal to 0. What's A and B? Number of equations equals number of unknowns, solve, right? And that's what we're doing. It's just got a bunch of exponentials in it. Sorry, question.
See, in the homework, it gives the definition of the log derivatives as the opposite. So.
Oh, I did the opposite? Yeah, I did that. So that's me being kind of dyslexic. I'm not really dyslexic. I accidentally flipped them. Okay. Yeah, sorry about that. Sorry about that. Oh, let me check the answer too to see whether I may have actually done it this way in the answer. In which case I wrote it down. Or it really doesn't matter. Right? It doesn't matter which one you do. Yeah. It's just that I try to remember it this way. It ends up being algebraically. It ends up being oddly slightly easier to do it this way. So yeah, this is also properly a log derivative, and that just has a little extra value. So anyway, so sorry about that. I didn't notice that. Okay, so let's go ahead and do this, guys. And once I do this on your homework problem, by the way, let me point out that where you solve the problem, when you're solving for energy. So what is this, minus A, and this is minus B, is that right?
Yeah. Okay,
and then that's A and that's B?
Oh, no, the other way.
Okay, wait. Wait, say it, sorry?
B and A.
B and A, right? What I'm doing now, you do here. To solve the homework problem, the boundary condition here is the one that solves it. This one just sets A and B together. Anyway, these are trivial. This is where you actually solve the problem. The boundary condition is here. Very similar to what I'm doing, almost exactly the same. Okay, anyway. Okay, so let's do regions 1 and 2 derivative. So just guide you what I'm doing. Let's see. Okay, region 1, the derivative would be kappa. And then, of course, we're at x equals minus a. Sorry for the people watching, minus a. Okay, kappa e to the kappa minus a, right? Because we're at minus a. Okay, it would help if I didn't forget the a. There we go. Okay. And now divide that by the wave function itself, e to the minus kappa a. And now you can see why I was saying it's actually, I need to remember to do it this way. You can see all this cancels, and now I've just got kappa, right? So that's why this is way easier to go. Okay, now let's do region 2, derivative over value. And that's going to be a little bit more of a Bismarcker. That's going to be ik. I can actually tell you, let me go ahead and do an algebra step. I'm going to get an ik out of both terms. So I'm going to go ahead and factor that. I'm going to end up with the b e to the ika. And of course, minus ika. Looking at my notes, I was like, wait, there's a minus sign there. And then the derivative brings down the minus ik. I've already factored that out, so that's minus c e to the ika. Okay, minus ikx, but x is at minus a. So, okay, I think I've done that right. And then you divide by the wave function. Now, unfortunately, you can see while you're in grad school, if I was an undergrad, if this was an undergrad class, I would have designed this. Like, you can see on the left how the wave function basically gets wiped out. Makes it easy. You'd hope that the same thing would happen on the right. It don't, because I've got b minus c, b plus c. So when you're doing grad level stuff and you see like, oh, wait a minute, shouldn't this cancel? That would make the problem easy. The answer is no. Welcome to grad school. It ain't that easy. Well, it ends up being, it is true that all of the problems you're going to have in your homeworks, the harder ones, are going to be about a page of algebra. If you don't run into a page of algebra, you're not doing it right. Bare minimum. Anyway, okay, so now let me just put down, so let's call this 1. Now let's do the derivative of 2 and 3 at x equals a. Oh, it bothers me that it bothers me it wasn't perfect. It needs to be perfect. Kind of. Okay, so what we get here is going to look really similar. You got to be a little bit careful about minus signs. So, and that's just because you're looking left of the origin, and then you're looking to the right of the origin. So the only differences are you're going to pick up a bunch of minus signs. So it should look the same. Expect it to look the same. And again, so now what I've got is a minus kappa. This makes me comfortable that I see a similar result on the first step, but it's not exactly the same, and it's different by a minus sign. That makes me comfortable. I know it should look something like that. Okay, like before, let me go ahead and factor out an ik. The top guy is b e to the ik. Since we're positive a, that's a minus, that's a plus. Again, look for that symmetry. Look for it to be basically the same. Minus ika, except that there's just a bunch of different minus signs. Okay, and then you divide by. It basically looks the same, except again, wherever there's an a, it's now the opposite. Plus c minus ika. Okay, and so this is 2. Okay. Again, I can't emphasize enough, this is basically when you do the boundary conditions for that inner little box, you're going to derive almost exactly the same thing. And notice that minus 2 is equal to 1. Okay, now at this point, something you also have to get used to is clearly, you know that you have these boundary conditions, and now you're probably at, and you whittled it down to this. You hope that it would simplify a little further, but it didn't. And double check yourself, no, this time, you know, oh, if this and this were the same, it cancel, but they don't. So, oh well. Now you can ask yourself, well, what the heck else should I do? And again, this is why I find these problems frustrating. Well, if this is kappa, if 1 is kappa, then minus is equal to -2. Now you have to have faith. What you do is you equate them and hope to God that something comes out that makes it solvable. Now I can tell you that it does because for one, I know the answer. Number two, because again, this is a system of equations. A, B, C, D. You're looking for 4 things, you have 4 equations. They have to resolve themselves. Okay, now the way that this works is, I'm going to do -2, ik, there's our little guy there, c e to the minus ika. Notice that I incorporated the minus sign by switching the terms. Over, I don't think I gave myself enough room, by the way, that was stupid. Okay, did I do that -2? You see, I just switched the terms. Yeah, okay. And then this is then equal to 1. And you can see that I didn't give myself enough room, so that was stupid of me. Let's see if I can get through this. B e to the minus ika. Oh, sorry for those of you watching on TV. Minus c e to the ika. Just had enough room. B e to the minus. Wait, did I do that right?
I have a question about the first set of equations.
I've got a mistake here. Don't I?
Yeah, the first derivative, where did the minus sign go? For phi 1 prime. So like AE to the, shouldn't there be a minus sign?
Wait, right here?
No, in the first one, where you take the derivative with respect to A, right? Shouldn't that minus sign come with it?
No, the minus sign comes from the position.
Yeah, my fault.
Yeah. But now I'm having, no, that minus sign, oh, no, okay, I did this one right.
You're fine.
Yeah, I'm fine? Okay. Yeah, it threw me off there. I double checked and triple checked this, but funny, that often means next to nothing. Sorry for squishing this together. Okay, anyway. So again, you have to have faith that this works. I'm sorry, my handwriting's a little crappy. Now, I swear to God, I'm not going to do this because I got to move on. At first, I look at this and I'm like, oh, you've got to be kidding me. And you're going to run into almost exactly this from your homework, but let me point out something really awesome. E to the ika, e to the minus ika times e to the ika is 1. Almost all the terms end up being 1. Sorry, about half of them. And then guess what? The times that you have e to the minus ika times e to the minus ika, which is e to the minus 2 ika, all of them factor out. So that's what's going to happen. It actually, as much as, so what you do is you bring this over here, you bring this over there, you cross multiply, and you just cancel on your terms. I swear to God, it is so simple. It's like 2 steps. End up with a b squared is equal to c squared. I swear in 2 steps, this turns into that. It's kind of cool to actually work it out because it's just incredible. It's neat. Anyway, if you think if that tickles you a bit, you belong in grad school. Okay, so now we can just decide, let's just make b equals 1, and then c is equal to plus or minus 1. So that's what you get out of that. And so what you have then are, therefore the wave function in region 2 is sine for odd or cosine, sine kx or cosine kx. So, okay, now what do you do with that? Remember I told you the whole point of this is energy. So let me show you what you do with that. What you get is a transcendental equation. A transcendental equation means that you have to solve it on a computer. That means that you've got something like sine of x is equal to x squared. You can't resolve that with like x equals inverse sine plus pi or something. It's unsolvable in terms of like a high school algebra sense. What you would do is you would plot sine x and x squared, and you look for where the lines cross. And that's the answer. And if I just shut over your head a little bit, I'll explain that in a minute. Okay, now what you do is you actually go back to the same equations above. You've got 1, you've got kappa. Actually, let's hold on. Let me go to. Let's do even. Let's do an even function, and let me go to. How do I want to do this? Sorry, I actually confused myself. What the heck is wrong with me? So what you do is, sorry, I just got flummoxed a little bit. So what you do is if you take the derivative of region 2, yeah, this works. Sorry, I'm being an idiot. Again, you kind of have to know what to do. Sorry, you're not going to look at equations 1 or 2. Okay, now if we have an even function, cosine, remember I said cosine is the answer, cosine Ka, we are, so if we had x equals a, the derivative of cosine is minus sine. And of course that will bring out a k in the process. And that would bring out, that means that's minus k, little k, tan sine over cosine is of course tan Ka. And this has to be, sorry, I'm being an idiot here. This is from, this actually has to be equal to kappa from, I think that's from, so I did region 3, this is region 2, right? So what have I done here? At minus a, I have to admit, I've gotten myself a little flummoxed here exactly what region I'm talking about. I think I must be talking about equation 2. Oh God, sorry, what the hell is wrong with me? Yeah. So, you know what this is? This is minus 2. Sorry. Should expect this kind of stuff to happen. This is complicated enough even I get confused. So I can see what happens is I've got a cosine over sine function in 2 equal to minus kappa. So notice that see what I've done is I've written down equation minus 2. So again, cosine over sine is what equation 2 is, but I put a minus in front of it, and so that's why it's equal to kappa. Okay, anyway, and I'll double check that after class. Now for odd, what you're going to end up with is, so you're going to start with sine Ka, and so the derivative of sine is cosine, k cosine, and that will be equal to minus kappa, and therefore what you've got here is well, here. Let me follow the same. This is cotangent. But sorry, that would be K cotangent of Ka is equal to minus kappa. Okay, let's go back up here. So you get two transcendental equations. So tangent of Ka is equal to kappa over k, little k, which is equal to square root of v minus e over e. And then for the other guy, what you end up with is cotangent. You may notice that this looks very similar to your, did I give you the answer? I gave you the answer on your homework, right? For the transcendental equations. I said, by the way, the answer is, I think I put that at the end of the question. And it looks almost identical to this. Okay, so now the way that this works is, minus, again, I want this to be perfectly symmetric, minus kappa over k, and that's, again, minus square root of v minus e over e. Okay, now what that allows you to do is remember that k is, let me just write this down again in case you forgot. K is square root of 2me over h bar squared, and kappa is square root of 2m v minus e over h bar squared. Now, one thing that I also, when I was working this out, although you see me getting a little bit confused what's what here, and I'll make sure I get that and let you all know in case I've done something wrong. Kappa over k, notice that I've whittled it down. That's completely legit. One thing I know you probably hate and I hate it too. What's the square root of 1 over x divided by the square root of x? I think it's 1. I don't know. That's my point. This over that is, in fact, v minus e over e, square root of v minus e over e. I hate those types of identities, but you'll run into them. When I find, and I'll leave hints on the homework and on whatever we have in the exam, if you run into one of these problems and you're not sure how things cancel, I'll make sure that you have some identities. But it does turn out kappa over k. The h's are gone, the m's are gone, because they're the same in both. And so, I know that a times b over a times c is just b over c. The a's cancel, but when you have a square root, it's just like, oh, what the hell? Anyway, so it ends up just being this. Now, as I mentioned, now you know that e is in here, and e is definitely in here, so what you end up doing to figure this out, here, I'll do it right here. As I mentioned, you actually have to now use a computer. And not tomorrow, but next week, I'll actually be doing some I'll be doing some MATLAB examples on how to solve some of this stuff, just for the heck of it. Now, if I'm going to actually, again, it's a transcendental equation, to actually solve it, you can't, again, there's no just saying, oh, E is equal to, hypertan of M, that's not going to happen. You have to actually have numbers. And so to make it remotely realistic, I have to do things like say M is the mass of an electron. I have to say that the length, and again, our problem goes from minus A to A, so 2A is equal to 1 nanometer. I have to say the potential is like 1 electron volt. And I hope that you realize that these are those are the kinds of things electrons run into. Electrons are in molecules that tend to be on the order of a nanometer, usually a bit less. Barriers electrons would run into would oddly be on the order of an electron volt. The mass of the electron would be the mass of an electron. And when I do that, I find 3 solutions. So there's only 3 down states. And above that, so there's a ground state and 2 excited states. The third excited state has an energy greater than the potential. And that means that there's no longer any quantum effects. There's no longer any quantum confinement. There's an infinitely allowed number of states above the potential energy. So you only find 3 discrete states, a ground state and 2 excited states. Now the even will be the ground state. And what you do is you have to plot from 0, this is E over V, 0 to 1. And again, energies above the potential, you don't go there because then you can fit any kind of wave. There's an infinite number of solutions. Okay, now if I plot tangent, I think it looks something like that. And then, so that's state number 1. Let's see, there's another, if I can recall what tangents look like, it looks like this. I think that looks familiar as a tangent function. Square root of V minus E over E for E minus V looks like this. So again, what you see are two states. Where those cross, those are your answers. Those are the allowed eigenstates, eigenenergies. And with those, you can define K. Now that you know the energies, you now know K. And you know A and B, and C and D. So now you have everything. Okay, the odd looks like this. So notice that this is state 1. This is the ground state. This is state 3. And so the odd one gives me my first excited state, which I call state 2. 0 to 1. Energy over potential energy. You can see why I made the barrier 1 eV, because this literally goes from 0 to 1, by the way. It's just a little trick I use. What you see is cotangent. Cotangent happens to look like this. Oh, actually, you know what? I'm sorry. I misspoke. There's actually 4 states. There's actually 4 states. And minus V minus this thing, of course, is negative. So that looks something like this. Okay, here's state 2, your first excited state. Sorry, there's actually 4. State 4. Okay. So anyway, that's how you solve that sucker. And so I have to look up where, I'll actually have to watch the video and see what I flummoxed there and make sure that that's -2. I got a feeling I got myself hopelessly confused. I'm fairly sure that's the right answer, but I may not have got to it correctly, so sorry about that. I really hate making any mistakes because I know when I was your age, as I mentioned now, if I'm, if a minus sign is missing or something, I tend not to worry about it. I usually can trust, if I'm at a talk or something, I'm usually just going to trust that the person did it right and maybe their finger slipped when they're writing an equation. When you're your age and you're trying to do a homework set or answer a question on a test and you're missing a minus sign, it's wrong and it drives you crazy if you're anything like me. So I try not to do that, so I'll double check that stuff. Anyway, okay, the last problem, let me introduce the problem because I know we'll end on time. And actually I don't need to say too much about this. What I'm going to do is I'm going to turn that potential energy surface. I'm going to turn that potential energy surface upside down. And this becomes, instead of a particle in a finite box, which again is a good representation of an atom. So if I give it more energy than an electron volt, the electron basically is ionized. So that's why it's like a good model for an atom. It's a crude but effective model for what an atom works like, quantized states and all that. When you take the potential surface and invert it, now you've got a scattering problem. Now an electron is going to hit a potential and bounce off of it, or it might go through. Now this, for any of you X-ray fans, again, there's a fair number of folks in our department who do X-ray science at Argonne. And, oh yeah, you do that too. I know what most of you do. So this is really quite relevant to what you do. This would represent X-AFs. If you don't know this stuff, don't worry about it. But this would be like an X-AFs, and this is your photoelectron hitting another atom. Sometimes it bounces off, sometimes it comes through. Anyway, for those of you who know what I'm talking about, there you go. Okay, so what you're going to have is, again, you have regions 1, 2, and 3. You're going to have an A wave, IK1X. Where this gets to be a bit of a pain is that we're going to have an IK1 and an IK2. Okay, in this middle region, we're going to have a C, E to D minus kappa, how do I want to do this?
Yeah, that's that.
Actually, what's that?
That's that.
You know what, you know how this is traditionally done? It's usually done like this.
That's if the energy is, each constant is 0.
What happens is that there's unfortunately two different sets of solutions where the energy is above or below. What you do is you make K2 for the energy above, you just make K2 imaginary, and it turns into an exponential.
That's for the energy constant V0, right?
If the energy is more than V0,
Then that's fine.
then what you do is you say K2 is imaginary, and this ends up becoming exponential decay. Okay, let me just write this down real quick. And so again, where this gets a little bit more complicated is that I've got two different types of Ks, and we're going to assume that this electron, this electron gets through the barrier, but just barely. Okay, so it's a very attenuated wave. And so in this region, we've got ourselves an E wave. And if it escapes, then it's just going to move to the right. Okay, so I just want to point out, I'm going to start here next time. I actually solved this on a handout for A, B, C, D, and E. I solved it all. It's about 5 pages of pure algebra. This is hideous. No doubt, but it is solved if you want to see it done. But anyway, I've gone over time, so we're going to do scattering next time. We're going to start there. I'm not going to do 5 pages of algebra class. I'm just going to show the result. But if you want to see it, it is on the website.